Hello, everybody. They say all is well that ends well. So today we end with Anna, Wysoczańska-Kula. She's from Wrocław, my hometown. They also say a friend in need is a friend indeed. So I must tell you that when I called Anna in the very last moment to ask her to give this talk, well, she just jumped into her Ferrari, drove at the top speed, and bang, here she is. Without any further ado, Anna, the floor is yours. Take it away.
Thank you very much. Thank you for the invitation, late but still a nice invitation for giving this talk. It will not be in the main flow of this conference. I'm going to talk about something at the crossroads of the quantum group and quantum probability. Yet there will be one rough algebra appearing, as you might maybe expect from the title already.
But I think as Ukrainians are higher on graphs, no? Check. Yeah. Okay. So.
Yeah. So there might be more. Yeah. So I'm going to talk about Lévy-Khintchine exposition for a very specific family of quantum groups, namely SP2N. This is a joint work with Franz Martin, and it's a nice opportunity to recall the results that already was found from like almost 2 or maybe more years ago, but recently we finally got our paper accepted for publication, so I will be able to give you at least some first details about it. So the problem I'm going to study and I'm going to talk about today can be stated in a very easy way. If we start with the universal algebra and we find a character on it, then we can set up 2 definitions. A linear mapping from this algebra to a complex number will be called a generated functional if it is normalized, so on the unit it takes value 1, if it is Hermitian, and if it is so-called conditionally positive, so it takes non-negative values of positive elements from the kernel of this character. And then such a generating functional is called Gaussian if it vanishes any triple products from this kernel of the character. And we are interested in finding a description of all possible generating functionals on a given augmented algebra. And since this seems to be quite difficult problems, at least in some cases, a kind of side question, which is supposed to help us to deal with the first one, is a question whether it is possible to somehow decompose a generating functional, any generating functional, into 2 parts. One will be Gaussian. So I should maybe say already now that these Gaussian generating functionals are kind of easy, more treatable than all of generating functionals, and to take out the rest. So this is the whole problem. As you see, we don't need much of theory to state it, but of course the motivations to study this kind of question there is behind it.
Sorry, I have a question. What is maximally Gaussian?
Yeah, so this I will explain during my talk, but in general, it means that in this part psi r, there is no more Gaussian. Yes, so you cannot decompose it further into something that is Gaussian and the remaining. This will come, okay?
So why is it called Gaussian? Okay.
Yes, why that was the question, why the name Gaussian. This will come with the motivation that I'm going to present. I just wanted to state this basic problem, so if you feel like sleepy, then you can keep the main problem in mind and fall asleep. But the motivations to study this kind of question comes from a non-commutative version of Lévy processes. Let me start from the very beginning. You might remember from probability classes the notion of Lévy process with values in Rn. This is a specific family of stochastic processes that is characterized by 4 properties. So it starts at 0 almost everywhere. It has stationary increments, which means that the law of the difference depends only on the length of the interval on which we take the increment. The increment has to be independent in the standard sense, and it has to have some kind of continuity, which is specified to be the stochastic continuity. So this is a family of processes that, on one hand, is like manageable. We can show many different results for them, but on the other hand, it represents a big variety of behavior. So in particular, this family contains Brownian motion, also Poisson processes, also compound Poisson processes, and so on. And I think I have one single picture for my talk. This is a variety of behavior we can see. So these are examples of paths of Lévy processes, and you see that we can have deterministic process, we can have a continuous path process, Brownian motion, and we can have like process with jumps, with random jumps, and we can have mixture of all of them. So this is really a family that is studied a lot in the classical probability. It has also many applications, for instance, to model some economical data. But if we want, and there is one more thing. In 1930s, Paul Lévy and Lévy-Khintchine independently, they proved a kind of characterization, a classification of how Lévy processes could look like. And to any such process, we can associate the so-called characteristic function. And this will be an exponent of this characteristic exponent function eta, which for Lévy process will always be of this form. So it will contain a linear term here, a linear term, a quadratic term, and an integral over some measure, which is usually called Lévy measure. And if you look more in a more careful way on how this function eta looks like, you can see that this part, in fact, this is the characteristic function of the Gaussian process. Well, actually, this part, the linear part, is the drift, so this deterministic term. And this part, it's usually called jump part. This is related to, well, this is the characteristic function of kind of mixture of compound Poisson process. So we see that for a Lévy process, the characteristic function somehow splits into the Gaussian term and the jump part that is related to Poisson process. And now there have been several notions, generalization of this notion of Lévy process, but basically, if we want to have the Lévy process with values in some different space, then since we need this kind of, well, an analog of zero, so where the process should start from, we need a neutral element. And also the composition rule requires that we have the notion of inverse and multiplicity. So this means basically that we need a group structure.
Yes, take a mic.
Yes, please.
So could you go to the previous slides? So,
Okay.
so in this case, where's the t from this process? If I look at this eta of x.
Yeah. So to each, well, each t will be of the form e times t eta or u. Well, the characteristic function of xt will be of this form, and this will be the characteristic function for x1. It's in one-to-one correspondence.
Okay, thank you.
Thank you for pointing. Okay, so now we can generalize the notion of Lévy process to some to have values in different objects, but this different object has to have a group structure. And for instance, in 1956, Kant proved a kind of analog of Lévy-Khintchine formula for Lévy processes on Lie groups, which, well, you don't really need to follow all the details, but you can see that the behavior is more or less similar. So we have, well, so the generating function of a Lévy process have this kind of linear term, the quadratic term, and the the integral over some measure. And again, if we study it in more detail, this part is related to the Gaussian process, and the remaining term is related to the Poisson, to the compound Poisson process. So we see the same kind of decomposition of the generating function. And of course, now we would like to pass to non-commutative mathematics, not commutative words. And a notion of non-commutative Lévy processes have been introduced by Akardi, Schulman, and von Waldenfels. But since we need to have this group structure at the range space, what is required to define a Lévy process is the star bialgebra structure on the space on which the Lévy process lives. So now a Lévy process will be a quantum stochastic process, which means that we take a family of star homomorphism going from a star bialgebra, so a space that has this group structure or the shadow of the group structure, to some non-commutative probability space, so a star algebra with a state. And this family should satisfy like dual properties to what we expect from a stochastic process to be a Lévy process. So it will start from the co-unit, yes, epsilon, our character will be the co-unit here. The increments we define to be the increments are these elements of the process time, and they should be stationary, which means that the distribution of these increments depends only on the length of the interval. The increments has to be tensor independent. Well, we have several notions of non-commutative independences, but here we, it can be shown that they more or less can be reduced to the tensor one. So tensor independence here means that the process for non-overlapping intervals will commute, and they will decompose under the state phi. And now, if we know that the increments are tensor independent, so in particular they commute, we can talk about composition of such increments. So the formula involves the co-multiplication here, and the convolution of two such processes will be again a random variable, which will be like again a star homomorphism. And we want that if we start from T goes to S and then from S to R, that we want it to be the same as if we started from T and go to R if we did. So this increment property is trivially satisfied in the classical case. Here we have to impose it as one of the conditions in definition. And again, we require some continuity condition. So these are properties that are dual to the classical properties of Lévy process. And
so wait, I'm a bit confused.
Yes.
Is A and B are non-commutative algebras?
yes,
So multiplication in B is not an algebra homomorphism.
So probably B and capital B and A should be
yes, sorry,
swapped.
this should be A. No.
So arguments are in where? In the probability
in A.
space.
No,
And
in
values
the
of J are in
algebra.
A.
So we decompose the elements by the commultiplication. So it should be in B.
And we multiply in B.
You want it to be commutative?
Well, I mean, I understood you, but you said that this is again a star homomorphism, and I don't believe it if B is non-commutative.
Why?
Well, because multiplication is not a homomorphism of algebra.
But well, you can check by hand that this. But you need to have this.
Okay, so it comes from.
Condition. Without it, it won't be.
Yes, so that's the okay. Sorry, yeah, I overlooked it. This you have this. Okay. Yeah, you have it. Commutation of ranges. That's enough.
So this means that that is partially defined. This multiplicative property is partially defined for pairs such that this J case of these B's do commute.
Yes, and so since you assume the independence,
such commuting things, it's a
this will
multiplicative.
be true for any J. Well, for any increment. Because here you see that there is an overlapping by 1 point. Maybe this should be open from one side. so that they do not overlap. They do really.
Okay, it's clear now from.
It's like you have a random variable, like from say a space to R. R is the A here, and then you take the dual space, reverse the arrow, so it's from A to some probability space.
No,
B.
that's clear.
Yeah.
That's clear. Yeah, thank you.
So now we would like to have also a classification of this, of all these Lévy processes for a given Starby algebra, which is our question. But well, and in general, it would be very difficult. But exactly as in the classical situation, we try to associate to a Lévy process something like a generator, and we will try to describe all these generators. So first of all, if we are given a Lévy process, due to the stationarity of the increments, we can define a semi-group of states. So phi t will be an increment of any length t, any increment of length t composed with the state of d. So this will be a state, and for any t, we will get a semi-group of states. And this semi-group of states will be differentiable at t, and the derivative at t equals 0 will be called an infinitesimal generator. And now it can be shown that a linear mapping psi is an infinitesimal generator of a semi-group of state whenever it is a generating functional in a sense that I gave you on the first slide. So it's permission, normalized, and conditionally positive. So it's basically straightforward to show that if psi is of this form, it will satisfy these properties. And to see the inverse, we just define the semi-group phi t to be the convolution exponent of t times psi, where the convolution is, convolution is defined in a standard way on psi, cancel psi, the multiplication. So to any Lévy process, we can associate a generating functional. Yes. Pardon? Well, this is a multiplication on T.
Yeah, so in
That's
the
a
previous
multiplication.
definition of a convolution, there was, as usual, multiplication.
This is the state.
Yes,
Okay.
MC.
Yeah, so we have multiplied.
Yes, you do multiply. Okay, and there is still, well, yet another object that we can associate to a Lévy process through this chain. So for a generating functional, which is a conditionally positive functional, we can do a kind of JNS type construction. So we set the inner product, well, semi-inner product, A times AB psi to be this. Well, maybe use this. We use this formula to define a semi-inner product, and then we define a space, a Hilbert space H, to be quotient space of A by the null space. And this way we get a triple that is called Truman triple, which consists of a unital star representation on the algebra, on some Hilbert space. Together with it, we can associate linear mapping, basically that is defined to associate to an element in A. Its class in this quotient space. And this mapping, it can be shown that this mapping will satisfy this relation showing how it behaves under multiplication. So it will be only linear, but it will be somehow under control as for how it acts on products. And then the third ingredient, which is in fact this generating functional we started from, is a linear Hermitian functional satisfying this condition. If you know Hochschild cohomology theory, this means that eta is the so-called one cocycle, and psi is a coboundary of the so-called cup product of two copies of eta. So from a Lévy process, again, we go to such a triple consisting of a representation, echo cycle, and a linear Hermitian functional, satisfying again this relation that shows us how it behaves under product. And Schumann showed, well, in 90th last century, that in fact there are one-to-one correspondences between all these stages. So from a Lévy process we can pass to a Schumann triple, but if we restrict to Schumann triple that are surjective, so that they satisfy this condition, then we can go back up to Lévy process using some reconstruction theorem. Actually, I should have made one more remark. Here we deal with pre-Hilbert spaces, but in the examples I'm going to talk about, we will work with quantum groups, and this pre-Hilbert space can be shown. Well, we can close this pre-Hilbert space and deal with operators on Hilbert spaces. Here, and this is what we are going to assume. Okay, so now if we want to describe all Lévy processes on a given star-by algebra, basically it's enough to describe all Schumann triples. And here, the problem I posed at the very beginning was really of an algebraic nature. We used only the augmented algebra structure. This is the same for Schumann triple. But in fact, if we want to keep this motivation coming from Lévy processes, so particularly if we want to go back and reconstruct a Lévy process from a Schumann triple, we still need this bialgebra structure and the commodification. But so the problem now is, since we want to describe all generating functionals, as I mentioned at the beginning, is somehow to study all the possible Schumann triples. So for that, we first of all need to know the representation theory of the bialgebra under consideration. Then we need to describe all these one cocycles, eta, which basically is the first Hochschild cohomology for a given Hilbert space. And then we need to check when such a pair can be completed by some linear functional to a Schumann triple. So that's this relation that I showed on the previous slide. So if this is the case, we will call eta completable. And then if we want to really describe all possible Schumann triples, then we will need to deal with some kind of freedom, namely any given generating functional can be associated to some given pair of a representation and a cocycle. Can also be general. We can add a drift term to it, and it will still be a generating functional. And a drift is a very easy generating functional that have this associated cocycle 0. So if we want to do this procedure to describe Lévy processes for a given star-by algebra, the most difficult part, apart from the representation theory, which can be tricky too, is the point number 3.
Sorry, who came up with this name, drift?
This again comes from the classical case. So this is this kind of deterministic part. Yes.
But he or she must have been a very good driver.
Okay. So to
I
see.
have a question.
Yes, please.
Why are you forgetting about the subjectivity of the Schumann triple?
Yes. So we assume that the Schumann triple should be surjective.
Okay.
Otherwise, you always restrict the Hilbert space. Yes. It means that you took that the space is too big and you just cut it. You need to cut. Okay. So to convince you that this question about completable is not that easy, I would like to show you what can go wrong. So if we are given a representation and a cocycle, because this is somehow where we stop for a moment, then to define a generating functional associated to it, we need to define it so that it is normalized, because this is what we require from a generating functional. And then due to the formula that I showed you before, this one, if the element A and B are from the kernel of the counit, the character epsilon, then these terms vanishes. And so psion AB, A times B, has to be given by the scalar product between eta. So there is a unique way to define psi on products of elements from the kernel of the counit. And such a mapping will be normalized and conditionally positive on the kernel of the counit, and well, will be conditionally positive in general and Hermitian on the product. But there is a potential problem that whenever we are able to write down the same element as two kinds of products, we need to have the same value of the scalar product, so that we have the unique way to define the mapping psion. And indeed, we can easily find an example of a very easy bialgebra. This will be a commutative algebra generated by normal elements, X, with the counit given by 0 on the generators. And then we can show that whenever we put two complex numbers, we associate them to X and to X star under the cocycle, this will define a cocycle. Well, this can be extended to a cocycle on the whole algebra, but a generating functional will exist if and only if that will be of the same absolute value W. Yeah, because otherwise, well, due to commutativity, psi on X star X should be the same as psi on X star, and we compute this should be.
Sorry, why not to demand compatibility between star and eta?
This is not how we
resolve
characterize
this
the
problem.
processes. I'm sorry, there is no condition we should have there. Yeah, indeed, we have no control on how the cocycle acts on the adjoint. Well, in general. Okay, so you see that already in some easy examples, this completability can be an issue. Yet there are some nice situations where there is no problem with completing a given cocycle. If we start with a representation, well, it should be a star representation, unit of star representation all the time. And we take a vector from the Hilbert space on which this representation acts. If we define eta to be a difference between pi on A acting on H minus epsilon on H, this will always be a cocycle, and it is called coboundary. It is somehow analogy. Well, in the classical case, this would be an analogy to a Poisson process. And there is always a generating functional associated to it, namely the one where we basically multiply eta, exactly what is in here. We multiply it by H on the column. And in here, since, well, this is the definition how it acts, there is no way there is any conflict appearing. So any coboundary, it's also sometimes called an inner derivation, will be completable. And even more.
Wait, is your A still this commutative algebra or bialgebra you had before?
No, this is
Generic.
full generality.
Full general.
A is a star bialgebra.
Just check.
Yes. And we can even make a stronger, show a situation which is a little bit stronger. Whenever eta is a pointwise limit of coboundaries with respect to the same representation, then it will also be completable, because if there is a limit of this kind of cocycles when H varies, then there will be also a limit of the generated functional data. So this kind of cocycles, which we call approximately inner, will also be completable. Okay, and now we are back to the problem of classification of Lévy processes, which we already know can be reduced to a classification of Schumann triples. And since, again, this classification in full generality due to this completability problem is quite difficult, we want to mimic the classical situation and ask, like Michael Schumann have asked in 1990, is it perhaps possible to decompose any generating functional into the part that is associated to Gaussian generating functionals that are quite, well, easier to deal with, and the rest. And see here, I just recall the definition you have seen on the first slide. So a generating is called Gaussian if it vanishes on the triple product. It is again like in analogy to the classical situation where Gaussian processes are, well, Gaussian generating function generators are vanishing on the, well, have zeros of order 2. Okay, and so such Gaussian generating functional we can also characterize in terms of the associated Schumann triples. Namely, they will be associated to cocycles having epsilon instead of the representation pi here. And in general, the associated representation has to be just the multiplicity of the counit. So these are kind of the easiest generators, well, generating functional possible. Okay, so now we can look on this problem of the composition of the generating functional from the point of view of Schumann triple. And again, to some extent, it's quite, well, some parts are quite simple, quite direct. So if we have a representation on a Hilbert space H, the cocycle and the functional, then we can always subtract a maximal Gaussian subspace out of the Hilbert space H. It will be a reducing space. So the representation pi will decompose into the part living on this maximal Gaussian subspace and the part, well, the rest. So this maximal Gaussian subspace is defined in a natural way because we know that Gaussian generating functional have the associated representation being just the multiplicity of the counit. So this is the unique space, well, the unique and maximal at the same time. So this is the natural definition of the Gaussian subspace that we should follow. So the representation will split, well, will decompose, and then the cocycle will decompose accordingly. So we can define the orthogonal projection onto this Gaussian subspace and project the cocycle onto it. And what we will get is a cocycle again, and it will be Gaussian cocycle. And the remaining part will be a cocycle again, but it will have no longer this Gaussian subspace. So we call it purely non-Gaussian. So we can do the first two steps. If we are given a generating functional and the associated Schumann triple, well, the associated Schumann triple means that we assume it is surjective. Then we can decompose the.
Sorry, Anna, just a silly question. When you say the associated Schumann triple, is it like some canonical construction? You have your generating functional, and then there's a unique way to have as associated Schumann triple, or you have some choices possible?
Yes, so this GNS construction will be
GNS construction
will be the
Okay.
canonical way.
Okay, good. Thank you.
Okay, so we can decompose the representation and the cocycle. And now the issue is whether we are able to decompose the generating functional, so the third level. And if it is possible, so that we can find a generating functional associated to this pair, so we can complete this eta G, and we can complete this eta R, so that psi altogether is a sum of the two, then we say that the functional psi admits a Lévy-Khintchine decomposition. And if this happens for any generating functional on a given algebra, we say that this algebra has a Lévy-Khintchine decomposition property. So if this kind of decomposition exists, then psi is the maximal Gaussian part in the sense that this part psi r has no longer Gaussian subspace, and this is unique up to a drift, which can be moved in between the two parts. Usually, one fixes it by choosing some projection on the certain subspace. Okay, but one can, well, it's quite direct to show that if we complete one of this pair, say the Gaussian part, then the other part, psi r can be defined just as the difference of psi and psi g. Yes. So if we know that one of this pair is completable, it means that that the Lévy-Khintchine decomposition exists. And so in the paper from 2015, Malte Gerholz, Uwe Franz, and Andreas Thom introduced 3 properties of the bialgebra that ensures that this Lévy-Khintchine decomposition holds. So if we complete any cocycle, then of course, in particular, we can complete both pairs. So the cocycle pi g, eta g and eta r, and so the Lévy-Khintchine decomposition holds. But due to this remark, the completability of one family is enough. So an algebra has the property GC if any Gaussian cocycle is completable, and the property NC if any purely non-Gaussian cocycle is completable. And any of the 3 properties are enough to ensure that the Lévy-Khintchine decomposition exists for a given bialgebra. And now I want to show you what happens for the case of SUQN. And there is a difference between SUQ2, which was treated by Michael Schumann and Michael Scheide in 1998, and the higher dimensional one. So maybe it's not necessary to recall, but by SUQ2, I mean a compact quantum group with the algebra, with the sister algebra generated by 2 generators satisfying these relations. There is a very well-known formula for the comultiplication. This is a graph sister algebra, as was shown by in the paper by Szymański. The paper has been cited several times during this conference already. And now I'm interested in the star bialgebra only. So I restrict my considerations to the polynomial algebra over SUQ2, which is a dense Hofstadter algebra in SUQ.
Anna, maybe if you allow me just a quick sad comment. Unfortunately, the coproduct is not easily expressible in terms of this graph algebra. It really sucks. So if you want the sister algebra K theory, that's the best presentation. We have it on the plate. But if you want to have quantum group structure, it's completely orthogonal.
Yeah. Okay, and the co-unit acts in the standard way, so it's 1 on the generator alpha and 0 on gamma. And what will be used for us if we study the representation theory of the algebra SUQ2, we find a 1-parameter family of 1-dimensional representations. These are among irreducible ones. So remember that you might remember that this quantum group is nicely expressed with the fundamental representation expressed in this way, if I remember correctly. So this representation on this matrix acts as epsilon theta on U, acts as E, right? E2 I theta, E2 minus I theta, and 0 out of diagonal, yes? So this is a nice family. It has the co-unit at 0, and as a function of theta, it is differentiable and even to infinity class. So now the idea, a remark made by Schumann and Scheide in their paper was that if we differentiate this representation pointwise at 0, then what we get is a Gaussian cocycle on SUQ2. And even more, if we differentiate it twice, then up to a constant, what we get will be a generating functional. Well, it will be a generating functional anyway, but it will be associated to this mapping, which I denote by epsilon prime, if we divide this epsilon over 2. So this gives us a nice example of Gaussian generating functionals on SUQ2. And it turned out that these are basically all can have. So any Gaussian cocycle on this group, on this bialgebra, will be of the form epsilon prime, so this specific mapping evaluated at the point A, times some vector from the Hilbert space of which our representation is. And it will always have, such a cocycle will always have a generating functional associated, and we can write explicitly how this functional should looks like. It will be related to this second derivative, epsilon bis, up to a constant, a positive constant, which in fact would be like a square of the norm of h over 2, if I remember correctly. And we can always add this term, which will be related to a drift. So
sorry, let me just double check that I understand you correctly. So for you, the SUQ2 Hopf algebra, you take its bialgebra structure in your general scheme of things. So what is this non-commutative probability space, this B, capital B?
Well, the point is that here we somehow shifted from the problem of Lévy processes to just functions to generate a functional, let's say, which are linear functions on P. Now, if you want to go back to a Lévy process, you have to reconstruct it, and then you can have different copies depending on your realization. Yes, you can have a Fock space, for instance, realization in Lévy process, so it will be unitarily equivalent.
And somehow,
so you don't really need to know what is the probability. Probability.
Now, should I read this remark or theorem actually that in this particular case, the information about the Gaussian cocycle lives in this classical subgroup of SUQ2?
That's exactly the case. So it lives on a circle, in fact, and it's the same phenomenon will appear in higher dimensions. So it will live on the on the Mach-Nautos. Yeah, that's exactly the case. Thank you for pointing that. Okay, so now since this remark shows that any Gaussian cocycle has a generating functional, it means that it's completable. And so SUQ2 has the property that I called GC, and hence it has this property of Lévy-Khintchine decomposition. So any functional can be decomposed. So this solves our question whether it's possible to decompose a given generating functional. But of course, it would be nice to know also what is this remaining part. And this was also studied by Schumann and Skyde. So they studied the non-Gaussian part, this purely non-Gaussian part. And here, if we take a representation that has no longer Gaussian part, yes, so this is this purely non-Gaussian case, and we take any vector from a Hilbert space on which it lives, then we can define a cocycle as a limit of coboundaries with this specific vectors HP as here. And one can show that these limits exist, so it properly defines a cocycle. This will be an approximately inner cocycle, which we know already is completable. So this is a class of purely non-Gaussian cocycles that are completable. And what was shown by Schumann and Skyde was that any purely non-Gaussian cocycle will appear in this way and actually will be uniquely defined by the value of this cocycle on the element alpha star. So this will be our H we should start in here to proceed. And since approximately inner cocycles are completable, it means that SUQN has also this property NC and allows the Lévy-Khintchine decomposition. Well, this we knew already from the previous slide. We can write down explicitly the associated generating functional, as I explained already before. This will be just a limit of generating functionals associated to this coboundaries. Okay, so for SUQN, we first of all know that the Lévy-Khintchine decomposition exists, and we know how to describe all Gaussian parts and how to describe the non-Gaussian parts. So basically, any generating functional, we can say it is of this form, like a sum of Gaussian and like limit of Poisson type processes, and they are parameterized by real number, a positive number, and some purely non-Gaussian representation together with a a certain vector from this representation. And now what we wanted to understand together with Franz, Martin Lindsay and Michel Spider was the case of SUQN for n at least 3, well, for n bigger than 2. So this, as a compact quantum group, this is defined to be built from a sister algebra generated by some n square elements satisfying unitarity relation and the twisted determinant condition. And the co-multiplication acts as in the standard way, knowing that U is a fundamental representation of the quantum. Still, this is a bit maybe, well, maybe not so tricky, but still we have a lot of Q commutation and commutation relations in this algebra. In fact, SUQN can be shown to be generated by this sort of relations. I don't write down all of them. And we will be interested again in the dense Hofstadter algebra of polynomial functions. This will be our Starby algebra under studies now. And in here, we also have one-dimensional irreducible representations, but they are more. So they are n-1. Well, we have n-1 parameter family, which means that again, if U is our fundamental representation, E, let's say theta with bar, meaning the tuple, acts as E to I theta 1, E to I theta 2, and so on, E to I theta n. And since the determinant has to be 1, this one of the constant theta has to be fixed to be the, so that the sum is 0. So this is again a family that starts, well, if all thetas are 0, that we recover the co-unit. And this family is again of C infinity class, or if we treat it as a function of theta j, a fixed theta j. So we can do the same trick as Skyde and Schumann did. So we compute the derivative at 0 in one of the directions. And each such derivative, epsilon prime j, will be a Gaussian cocycle. And of course, a linear combination of Gaussian cocycle will be a Gaussian cocycle again. And again, if we take the second derivative with any two different, well, any two directions, possibly different, we will get a generating functional. So these are, well, we got a bunch of examples of Gaussian cocycles and Gaussian generating functionals. Now the point is that we can show, similarly as in SUQ2 case, that any Gaussian cocycle will be a linear combination of epsilon primes with different j's. And we can show the general formula for a generating functional, which will be a linear combination of all these functionals that we have here. The point is that it's no longer true that any Gaussian cycle will give rise to a generating functional, because this will happen if and only if we have this Hermitianity condition on eta, which basically means that eta will have, well, eta given by this formula will have the will admit a generating functional whenever the vectors aj satisfy the, well, the condition. So hk is hk. Well, so the inner product is real. If it is not, it's of course easy to find such examples, then we don't have a generating functional associated to this Gaussian cocycle. So we see that contrary to the SUQ2 case, SUQN for n at least 3 does not have this GC property. Well, still, this does not mean that the Lévy-Khintchine decomposition is not possible, because we can try to see what happens with the non-Gaussian part. And for that, we need to recall that we can look at SUQ n's chain, the chain of quantum groups, as a chain of subgroups. So SUQN has as a subgroup SUQN minus one or any smaller dimension, but crucial for us will be this epimorphism from SUQN to SUQN minus one.
I guess you forgot the symbols of algebras around SUQN and SUQN minus one.
So the curly SUQN is the polynomial algebra.
Ah,
That's a
okay,
different
but
one, yes.
that's very
So
confusing.
I should have specified that earlier. Yeah, so these are just by algebras. So the way how the smaller group sits in the bigger one is shown on the fundamental representation. So the last row and last column will be sent to 0, except for the diagonal term that will be sent to 1.
Yeah, sorry for being so picky, but if these are really algebra, so what's the meaning of single element equal to SUQ1? That's an algebra.
Yeah, that should be
That's, at least it's contradictory.
polar. Yeah. Okay, and now we say that if we are given a linear map going from SUQN to some vector space, that it lives on this smaller subgroup if it factorizes for this epimorphism Sn. And we will use it, for instance, to say that a representation on SUQN lives on a smaller, on a subgroup. And this factorization basically means that elements that are sent to 0 will be sent to 0, well, under this Sn will be sent to 0 by this representation, and the element that is sent to 1 will be sent to identity by this representation. And by the unitarity condition, we can see that being 1 on this bottom right corner of the fundamental representation is exactly equivalent to a representation living on this smaller sub. Okay, and now we want to treat a purely non-Gaussian cocycle. So we take, first of all, we take a Schumann triple. I should have assumed maybe that pi is purely, well, is purely non-Gaussian. And we want to understand whether it is possible to associate to such a pair generating function now. And for that, we proceed by induction. First of all, we I wanted to explain all the steps in the proof, but maybe I'm running out of time. So
7 minutes.
Maybe I just pass you the main idea. So the idea is that we decompose the whole space into the part on which we are going to work a little bit more, and the part which we show is in fact something living on a subgroup. So then if we deal with what happens on this left-hand side, and if we show that over there we can complete our cocycle, then we can basically proceed by induction. Yes, because on the right-hand side we have the same situation, but on the dimension of a lower, on the lower quantum group of lower dimension. And what we are showing is exactly similar, although more involving to the idea of Schumann and Kreide. Namely, we show that this part on the left Rn, the representation decomposes accordingly, and then of course the cocycle will, denoted this way, will decompose. Yes, so the cocycle on this left part, left-hand side, is approximately inner. So we can we show that we can always define a certain limit, and it will be exactly this equal to our cocycle. And since approximately inner cocycles are completable, this means that this part, this cocycle on the left, can be completed. And since the right part about the right part, we know that all this leaves off on SUQN minus 1 and capital N minus 1, then we can proceed by induction to show that we decompose the cocycle into N minus 1 pieces, and each of this piece, in fact, is approximately inner, so it will be completable. So this shows that SUQN for n bigger than 2 has the property NC, and hence admit the Lévy-Khintchine type decomposition. And since we more or less know how the Gaussian part and the non-Gaussian part looks like, we have a classification like the Hunt formula. So here there's one thing I have to, I would like to emphasize. It's no longer, it's no longer true that any vector in the Hilbert space H will give rise to a cocycle. Basically, we can show, let me skip this, but we can find an example already in SUQ3, and then, of course, embedded in higher dimensions of a representation and a vector that give rise to no cocycle. But still, we know that many vectors will define cocycles on this SUQN. And actually, we need to take some closure with respect to this specific norm. And any element in this closure will parameterize the generating functionals in general. So more or less to sum up, there are several differences between SUQN case and the case of higher dimension. So SUQN has the GC property, which is no longer true for n bigger than 2. In both cases, the non-Gaussian cocycles are approximately inner. In fact, we can, for the higher dimension, we can show this, that there is a direct sum structure. So both algebras have NC property, but the parametrization space is different between these two cases. So once we may use all the space, the representation space, and on the other, in the other case, this space is smaller. But both bialgebras have, pop algebras, in fact, have the Lévy-Khintchine decomposition. So I would stop. Well, I might stop here, but since I still have 3 minutes time, I don't want to leave you with maybe an idea that all bialgebras will allocate a composition. Because this might be the impression after my talk. For SUQ2 and SUQN for bigger n, we do have the decomposition, and in fact, we know a lot of examples of bialgebras, mainly coming from quantum groups, because we were mostly interested in this in the specific case, that do admit Lévy-Khintchine decomposition. So, of course, all commutative bialgebras, that was the first result proved already by Schurman, but he also generalized it. Well, he also showed that the so-called Brown algebra has this property. Brown algebra is like almost like a unitary quantum group, except this is just a semi-group with no antipode. And then the result for SUQ2 was shown in 1998 by Dan Schurman, as I mentioned. Since then, more examples have appeared. So we know that the composition exists for the free permutation group. Actually, it exists in a trivial way because there are no non-zero Gaussians there. It also exists on SD+, I guess in the similar way or more or less similar. Also, this decomposition exists for the so-called universal quantum groups, provided the matrix that defines these quantum groups has some properties related to eigenvalues. And what I showed now was the case of SUQN, and the same idea basically works for UQN. But already in 2015, Uwe Franz, Malte Gerfold, and Andreas Thom gave the example of a bialgebra which do not have the Lévy-Khintchine decomposition. This is a group algebra of the fundamental group of an oriented surface. And also in 2018, together with Bifurov Das, Uwe Franz, and Adam Skalski, we found that the free unitary and free orthogonal quantum groups starting from some low dimension, do not have Lévy-Khintchine decomposition. So it is not evident that every star bioalgebra do have it. Of course, it would be interesting to understand the idea why some algebras do not have this decomposition. Until now, we worked more like case by case. And the situation is even more difficult because we don't have any kind of hereditary properties. So this property it is related to homological stuff. So one should not probably expect any kind of this behavior. Still, it would be nice to have some conceptual idea what happens in here. And so let me finish by some references, and in particular the paper that my talk was based on. This one that hopefully will sometime appear in the journal. Thank you.
Thank you so much, Anna. Wow, perfect. All right, any questions? Go ahead.
Yes. So in the example of free quantum groups, if you can put the slides. So I don't understand the no case, the red line. This is not a special case of the one before.
Well, yes. So UN plus, say, is U identity plus, yes, F being identity. But this situation holds only when F star F has eigenvalues of multiplicity one only.
Sorry,
Whereas here we have
the,
integral multiplication.
No, I read the value equal to one, not multiplication. Thanks.
You said something about the Gaussian part living on a subgroup. So are these subgroups known?
Yes, so for SUQN, the Gaussian part lives on the maximal torus. Yes, so it will be n-1 torus. In general, there is in general, it's not known. There is a paper by Uwe Franz, Henri Prelon, and Adam Skalski, who studied the so-called Gaussian part of a quantum group, which is the part of the quantum group that can be seen through Gaussian generating functionals. And in general, this is included in the cut case, if I remember correctly, but it may be different.
Okay, thank you.
So if I could continue this question. So this classical torus inside of a quantum group, this has this property that the neighborhood of the neutral element can be filtered by these powers of this augmentation idea. Demanding this for a non-commutative group, quantum group, is strange because even forgetting about this quadratic part, if you think about the linear part, so classically, if you take this kernel of this augmentation and you divide it by the square, it is the space of linear functionals on the Lie algebra of a group. So quantum groups do not have Lie algebra. Okay, so
No, but I said it's not a general result. It's specific to SUQN that Gaussian parts Gaussian functionals live.
yeah, but your initial definition was quite general.
Yes.
This was
But it doesn't tell you anything about living on a classical subgroup or not. It's not. Well, in this paper
so
by
everything is
Franz Prelon,
relative to this, let's say, maximal classical torus.
But in this case,
No. So everything, all results you presented are under this assumption that you restrict this condition for being Gaussian to a classical torus.
no,
Inside.
but this follows from the relation we have in the group in the algebra.
So I don't
So
understand
let
this.
me maybe go back to one of the cases we had. So in here, yes, we have for maybe as you could will be here. So in here, we have this one parameter family that lives on the torus, and it was just shown that this is enough to describe all Gaussian generating functional. If I remember correctly, in this paper by Franz Frelon and Skalski, there are examples of quantum groups with Gaussian part being non-classical. Well, I think even this free unitary group, maybe it's not.
Is it so only for SUQ2 or for SUQN also?
This works, well, the same idea works for SUQN too, well, for SUQN as well. But this follows from the relation we have in the group. It's not a general statement.
Anybody else? Anybody from Zoom? Okay, so let me finish by asking you some very naive questions. Yeah. So what happens when you vary your Q? Because as everybody knows, when you take a look at the sister algebra of SUQN, it's insensitive to the value of Q, but the quantum group structure is, right? So what happens to your theory, to your results, if you vary Q? These are different quantum.
Yeah, I'm wondering. Because of course these results are true for Q between 0 and 1.
Yes,
So
yes,
this
yes,
limit
yes.
cases can behave differently. Also
Yes.
in -1 case, it's different. Actually, well, we do use well, it doesn't really seem to depend on Q.
Yeah.
But I would need to think maybe more about it, but yeah, maybe an interesting idea.
So one more thing, I mean, does Q really need to be different from 0? Because the co-unit will still exist and you somehow don't really use much
Yeah, well, it's
the other structure.
it's not here, but in the calculations we do use the fact that we can invert the operators. Well, that the operator 1 minus Q times, well, pi on U, say NN, that this will be an invertible operator. And if Q, well,
If Q is 0,
then
it's good.
still it will be an invertible operator. Okay, I think I would need to think about it.
Yeah.
I have the impression that for Q equals 0, it doesn't
Well,
really
I think
work, but I'm not sure about it.
it's involved in, we have to this construction relies on to understand the representations of this algebra, which somehow depends on like how to
Mhm.
find all the irreducible representations of this algebra. And this part depends on
Well,
Q.
the representations that actually extend to the C-star algebra don't depend on.
Yeah.
So
No, so
that's the point. Are there ones that are just the representations of the dense subalgebra? There is
Yeah.
correspondence, and what happens at 0? Well, I get it.
Okay, anyway, it seems like a topic for further debate, and it's a time to wind it up. So let us thank Anna for her very beautiful talk, for telling us how to drift, which we much appreciate. So thank you so much. It's been great. So now I stop recording, but please come down here for the picture.